My name is Sergei ELISEEV, and I am the head of the computer vision 3D reconstruction research group at Yandex. Today we are going to talk about how to create a production-ready solutions for volumetric and 3D capture, and at the same time don't burn out all the money of your investor or department. Volumetric content is becoming very popular across many industries. In the gaming world, it can be used to build lifelike characters and even drive animations. In the VR industry, volumetric content opens the door to fully immersive experiences. High-realism Gaussian Splatting scans or their mesh equivalents can be very useful for creating shots in big-budget films, especially when you need freeze frame or orbiting camera effects. But there is one big problem. The cost of volumetric production is still very high. So I'll explain how we managed to bring those costs down. Usually, the creation of a volumetric video starts with an estimation of geometry. To work with a good quality, lots of cameras are needed, sometimes even hundreds of them. Once the geometry is extracted, it's converted into a mesh and then textured. Precise segmentation is also needed to separate the objects from the background. Traditional volumetric rigs rely on heavy, rigid frames to keep all the cameras perfectly aligned, because even a tiny shift can ruin the reconstruction. Our goal was to democratize this process by building a lightweight, portable system. In a baseline of our method, we supervise with two simple losses: color and geometry. We fire rays from all cameras at once. As a result, we get a reconstruction approach that starts delivering solid geometry with as few as 7 cameras. We adapted the volumetric renderer. When computing a character's color weight, we now account not only for that character's own density, but also for the densities of the others. Segmentation is learned implicitly. If a person network catches the background, neighboring cameras penalize it. If a background network catches a person, adjacent frames in time penalize it. By improving the algorithms, we made our setup work with just a small number of cameras, handle dynamic backgrounds, and avoid expensive manual labeling. Even though we achieved strong geometry, the textures were still blurry. To fix textures, we used differentiable rendering with camera poses. We placed April text in the scene and tracked how they moved over time compared to the calibration moment. You can see they moved by several pixels from calibration point. Pose refinement. More concretely, using the April text, we solved for a small rotation delta and the translation delta for each camera. Our simple low-cost cameras were not synchronized, they didn't have gain lock. We've solved this problem in that synchronization accuracy reached about 1 millisecond. We used video frame interpolation methods to generate images for all cameras, as if they were captured at the same moment in time. You can see how much better the fingers are reconstructed now. As a result, by replacing some of the traditional hardware solutions with software algorithms, we were able to build a volumetric capture studio that works with simple, low-cost cameras, requires no dedicated studio space or heavy structural frame, fits into 2 suitcases and can be assembled in just 4 hours. But there is one more thing. We've asked to deliver close-up ready static reconstruction for film and ads integrations. Our original pipeline wasn't a perfect fit. We needed a more portable setup and higher detail. Human hairs, for example, is notoriously hard to represent as a mesh. For this use case, Gaussian Splatting is a better match. It preserves fine, soft structures like hair, while staying lightweight and portable. We tackle this by building our new rig and software. Instead of hundreds of cameras, we orbit the person and trade camera count for capture time. The result? 15 off-the-shelf cameras and 12 seconds for a single pass. Even over such a short window, and even if they hold their breath, people still move a little. That tiny motion causes artifacts. We split the picture on a grid of separate cameras, each with own extrinsics and intrinsics. And during the fitting of Gaussian splats, we fit not only the splats but the parameters of the virtual cameras. You can see the difference. The bonus of having a good Gaussian splatting reconstruction is that you can easily extract the geometry. We are able to extract fine geometry suitable for animation. We have shown that with talented developers and smart algorithms, you can replace much of the expensive hardware. I hope you can apply this approach in your own projects.